Hello, this is Richard Hammock's Calculus 1 course. We are in part 3 of the course on derivatives. In lecture 16, we defined a derivative of a function, which is one of the key concepts in calculus. And the derivative was defined as a certain limit. In lecture 17, we began to develop a list of rules that allow us to find derivatives of certain functions without a limit. And we will continue with that list of rules, but today we pause to look at some important notation and examples involving the concepts we've already learned. We'll break this up into two parts, lectures 18a and lecture 18b. I'll begin with a recap of the previous lecture, or the previous several lectures. Remember that the derivative of a function f of x is another function f prime of x defined as f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. You can also express this as the limit as z approaches x, f of z minus f of x over z minus x. And each of these limits gives the slope of the tangent to y equals f of x at the point x f of x. So the picture is this. If you have a function y equals f of x, take a certain point, x f of x, on the graph, look at the tangent line, its slope m will be f prime with this particular x value plugged into it. Notationally, we often write f prime of x as d dx of f of x, which we could read as the derivative of f of x. And then we develop some rules for computing derivatives in a way that bypasses the limit definition, provided that the function f has the right form. The derivative of a constant is equal to 0. The derivative of the identity function f of x equals x is equal to 1. The power rule, which states that the derivative of x to the power of n is n times x to the power of n minus 1. The constant multiple rule says that the derivative of a constant c times f of x is c times the derivative of f of x. And then the so-called sum difference rule that tells us that the derivative of the sum or difference of a sequence of functions is the sum or difference of the derivatives of the individual functions. And using these rules in conjunction, we can very quickly find derivatives of lots of different functions without using a limit. For example, if we have the derivative of 5x cubed minus x squared plus 4x minus 7, the sum difference rule tells us that this derivative is going to be the derivatives of these individual functions, added and subtracted together according to the signs. So the derivative of 5x cubed by the constant multiple rule and the power rule is 5 times 3x squared. The derivative of x squared by the power rule is 2x. The derivative of 4x is 4, and the derivative of 7 is 0 by this first rule. So we get, in 2 steps, or probably even 1 if you're doing this from scratch, 15x squared minus 2x plus 4 as our derivative. Let me say a few words about notation. Remember that if y is equal to f of x, then the derivative f prime of x can also be denoted as y prime, which makes sense. If y is f, then y prime should be f prime. And we also denote this derivative as dy dx. And remember where this notation comes from. Dy dx, it's just a notational package that stands for f prime of x. But you can think of it this way. If
if you have the graph of your function y equals f of x, dy dx can be thought of as a rise dy over a run dx on the tangent line to the graph at the point x. So dy over dx equals the slope m, which is f prime of x. So dy dx equals f prime of x. So it's very suggestive notation, although for the most part you look at this symbol dy dx as just standing for the derivative f prime of x. But it does have this nice geometric interpretation. So f prime of x is also denoted as dy dx. We sometimes write dy dx as df of x dx, because f of x equals y after all. But more commonly, we'll just say that's ddx of f of x. In this sense, ddx is like a verb. Take the derivative of f of x. That's what this says. You could write that as ddx of y. And sometimes in other texts, you might see this as big dx of f of x. All of these are different notations that stand for the same thing, the derivative f prime of x. So for example, if we had the function y equals f of x, which is x cubed, then f prime of x is 3x squared by the power rule. And we would also write that as dy dx equals 3x squared, or y prime equals 3x squared. A derivative is a function, so you can plug in values. For example, taking f prime of 2 would be 3 times 2 squared, which is 12. But then what about dy dx? What if you wanted to plug in the 2 to dy dx? There's no place to plug in the x. So here's the way we overcome this notationally. If we wanted to plug in x equals 2 to dy dx, we write it this way. dy dx with the bar subscripted with an x equals 2. And we read this as dy dx at x equals 2. And it stands for what you would get if you plugged in x equals 2 to the formula for dy dx. You get 12. Likewise with the y prime, if you wanted to plug in a value like 2 to that, you would say y prime at x equals 2. It's 3 times 2 squared, or 12. So you'll see this type of notation showing up later in the course. Maybe not so much now, but later in this chapter and in subsequent parts of the course, you'll see this. Of course, the variables could be different. For example, if we have a function z equals g of u, whose picture is like this. You have a u-z axis, and here's the graph, z equals g of u. Its derivative would be g prime of u, which we could also write as z prime. Or, alternatively, dz du. So again, dz du is like a rise over a run on this tangent line. That would be the slope of the tangent line, which is g prime of u. So all of these things are equal. So g prime of u, also denoted as dz du. You could write it as dgu du, kind of like what we did over here. But more commonly, you would say ddu of g of u, which stands for g prime of u, or z prime, or dz du. Or ddu of z, or du of g of u. This is entirely parallel to what we did up here, as long as we substitute or change the variable y to a z and the variable x to a u. It's exactly the same thing as we had above. So for example, if you had a function z equals g of u, which happens to be the function u cubed, you would say g prime of u is 3u squared, or dz du is 3u squared, or z prime is 3u squared. So g prime of 2 would be 12, dz du at u equals 2 would be 3 times 2 squared, it's 12. Or z prime at u equals 2 is 12. So for the most part, in lecture, I'm going to stick with the variables y and x, but not always. In many situations, different variables will be used. For example, if you had a problem involving time t, the variable might be t for time, and so on. A few warm-up examples. If we have the function w equals 3z to the 10 plus z plus 2, its derivative could be denoted, or would be denoted, dw dz, and by the power rule and the sum difference rule, that's 30z to the 9th plus 1. Here's another problem. Find the derivative of the function y equals the quantity x cubed minus x squared times the quantity x squared plus 1. This expression doesn't quite fit any forms for the rules that we have so far. We don't have a rule for f of x times g of x yet. We will have one later, but we don't have it right now. So none of the rules apply. But you'll find that this happens often. By a simple algebraic manipulation, you can change a function into a form to which the rules do apply. For example, for this one, you could FOIL it out to get y equals x to the 5th plus x cubed minus x to the 4th minus x squared. And then you could find the derivative of that using familiar rules. dy dx is 5x to the 4th plus 3x squared minus 4x cubed minus 2x. So watch out for this. It's sometimes necessary to change a function slightly using algebra to get it into a form to which the rules apply. If we had the derivative of 5x to the 5th plus 3x cubed minus 4x over 5x, that's a quotient of two functions, and we don't yet have a rule that tells us how to find the derivative of a function f of x divided by another function g of x. But we could use the rules that we do have to algebraically manipulate this into something that we could deal with. For example, the function we're taking the derivative of is 1/5 of this fraction. We're just taking the 5 out as a 1/5 to the side. And now if we look at this, that 1/5 could come out of the derivative using the constant multiple rule. And also, what about the x in the bottom? Notice that we could factor an x out on the top from every term and cancel with the x in the bottom. So that 1/5 comes out, we factor an x out of the top, and now cancel these x's. And we've changed the problem to 1/5 ddx of 5x to the 4th plus 3x squared minus 4. And that we can use our rules for. We have 1/5 times this derivative, which is 20x cubed plus 6x minus the derivative of 4, which is 0, giving us 20x cubed plus 6x over 5. So there's our derivative. We'll move on now. In this next example, we're illustrating an important process that you'll see a lot of in part 4 of the course when you get there. The problem here is to find where the tangent to f of x equals x plus 9 over x is horizontal. In other words, where it has slope 0. So here's the picture. Our function f of x equals x plus 9 over x looks like this if you graph it. And we're looking for the values of x for which the tangent line is horizontal, has slope 0. And you can see it looks like from this function it would happen in two places, here and here. So the question is, what are these x values that lead to a horizontal tangent? Well, the derivative gives us the slope of a tangent line. So here we're basically asking for what values of x is the derivative of this function equal to 0, where the slopes are 0. So to answer that question, we could find the derivative and set it equal to 0 and solve. Now, if we're finding the derivative of this f of x, we'd first want to write f of x in a way for which the derivative is easy to calculate. Write it as x plus 9 x to the power of minus 1, so we're primed here to use the power rule. And now our derivative is f prime of x equals 1 minus 9 x to the power of minus 2, when we use our rules here. And that's 1 minus 9 over x squared. So we're looking for these two values of x for which this derivative f prime is equal to 0, giving a slope of 0. So we're going to take the equation f prime of x equals 0, which is this expression, set equal to 0, and we're going to solve it for x to find these values. You could add a 9 over x squared to both sides and now cross multiply to get x squared equals 9. And taking the square root of both sides, you get x equals plus or minus the square root of 9, or plus or minus 3. So the answer to our question is x equals 3, or negative 3, would make the tangent line to the graph of the function horizontal, as we see here. Answer: tangent is horizontal at x equals 3 and x equals minus 3. As I said, you're going to see problems like this in part 4 of the course when we start talking about applications of the derivative. And you'll find that in part 3, where we are now, you'll see many questions that ask you, find where the tangent line is horizontal, or maybe where the tangent has some specified slope. And you just take the derivative, you set it to the slope you want, like 0 in this case, and you solve it. It's good to work these problems, and you'll see more problems like this as we develop more rules. In the next example, I'm going to illustrate another useful process that, again, you'll find yourself carrying out in part 4 of the course. Here we want to find the equation of the tangent line to the graph of the function f of x equals 5 plus 6x minus x squared at the point 2, f of 2. And f of 2, if you work it out, is 13. So we're talking about the point 2, 13. So we're not looking for the slope of the tangent line, but the actual equation of the tangent line. Now the tangent line is a straight line. So it's the graph of a linear function y equals mx plus b. So that's what we're looking for. Y equals mx plus b with a specific m and a specific b. So let's think about how we would solve this. Well, first of all, think of the graph of our function f of x. If you graphed it carefully, it would look something like this. It's a parabola that opens down because you have the negative x squared term. And if you plug in 2 to this function, you get f of 2 is 5 plus 6 times 2 minus 2 squared. That's 13. And there's a tangent line to the graph at this point, drawn in red, and we're trying to find its equation, y equals mx plus b. So let's think about how we would do that. If you're finding the equation of a line, there are a number of formulas that you could use for that. And here we have a point on the line, 213, and that might suggest that perhaps we could use the point slope formula for the equation of a straight line. And you should be familiar with this from pre-algebra. We have this point on the tangent line, x naught, y naught, which is 2 f of 2, or 213. That's our point. Now for the point-slope formula for a straight line, you also need the slope of the line in question. And remember that the slope is given by the derivative. The slope of the tangent at any particular point x f of x is f prime of x. Now f prime of x, we can find that that's 6 minus 2x using familiar rules. This 6 minus 2x is a function of x. It gives the slope of the tangent at any given point x, f of x, but we're interested in a very specific point where x is equal to. We want the slope of that particular tangent line. The slope of the tangent at this point 2f of 2 is f prime of 2, which would be, let's see, 6 minus 2 times 2, or 2. So the slope of this tangent line is m equals 2. And that certainly looks right. Rise over run, it looks like the run is half of what the rise is. So that would be slope 2. So we've got our information, the data we need. We have a point on the line that we're trying to find the equation for, and we've got its slope. And that can feed into the point-slope formula for a line with slope m passing through the point x naught, y naught. You'll remember that that formula is y minus y naught equals m times x minus x naught. Plugging in the data, y naught is 13, the m is 2, that's our slope, and then x minus x naught is the number 2. So we get y minus 13 equals 2 times x minus 2, distributing that 2n, y minus 13 equals 2x minus 4, and then adding the 13 to both sides, we finally get our y equals 2x plus 9. That's a y equals mx plus b. That's the equation of our tangent line. So this tangent line is the graph of the equation y equals 2x plus 9. You can see there the slope is 2, and the y-intercept is 9. That would be right here, and that looks about right. If this is 13, 9 is there. So there's the answer to our question. The equation of the tangent line is y equals 2x plus 9. So as you're working exercises in this section and in subsequent sections, you'll see questions saying find the tangent line to the graph of this particular function at some particular point. And you could carry out that process this way. You'll be getting a lot of practice with this. It's very good practice because in part 4 of the course, there will be certain places where you do need to find equations for tangent lines. It's good to get that practice now. Here's another example. In this example, we're going to be thinking of the derivative graphically. Consider the function that's graphed here. And I've been careful to write this very generically. It's just a function y equals f of x. There's no formula given. So the function y equals f of x is just described by its graph. And what we want to do in this example is sketch the graph of the derivative f prime of x, the derivative of this function given here. So there are no rules that we can apply. We don't even have an algebraic expression for f, so we can't evaluate a limit to find the derivative. We're going to do this the only way we can, by looking at the graph geometrically. You might think about solving this by making a table where you pick a sequence of x values, say -7 up to +7, for this x value up to this one. And for each of those, we'll think about the corresponding f prime of x value and see if we can figure it out. And that'll give a bunch of points on the graph of f prime of x, and we can plot them and see what the graph looks like. Let's start with -7. So at x equals -7, we want to know what is f prime of -7? Well, that would be the slope of the tangent line at x equals -7, and the slope is clearly 0. So f prime of -7 is 0. And we're going to go ahead and plot that point -7, 0 right there. So that's on the graph of f prime. Moving on to x equals -6. Slope there is 0. So f prime of -6 is 0. And we'll plot that point -6, 0. Move on to -5. At -5, the tangent line is still 0, slope 0. So f prime of -5 would be 0. And we'll plot that point -5, 0. Moving on to -4, same thing. The tangent line has slope 0 at -4. So f prime of -4 is going to be 0. Let's go to -3. Oh, we plot that point right there. And go to -3. Now our tangent line has a positive slope here, and just to estimate, it looks like the slope would be 1/2. The run is twice as long as the rise, thereabouts. So f prime of -3 would be the slope of this tangent line, which is about 1/2, so 0.5. So we'll plot the point -3, 0.5, and that's on the graph of our derivative. Going to x equals -2, it looks like the slope of the tangent line there that's like slope 1. So f prime of -2 is somewhere around 1. And we're going to plot the point -2, 1. That's a point on the graph of f prime. And move over to x equals -1. You look at the slope. Looks like slope 1/2 again. So that would mean f prime of -1 is -1/2. And we'll plot the point -1, f prime of -1, right there. -1, 1/2. And move on. Now we have x equals 0. And look at this. The tangent line to the graph of y equals f of x is horizontal. Its slope is 0, telling us that f prime of 0 is going to be 0. So we plot the point 0, 0. And then continue to x equals 1. Now the tangent line is negative slope. And it looks like, estimating here, rise over run is -1/2. So f prime of 1 is -0.5. We're going to plot that point 1, -0.5. Move on to x equals 2. Looks like the tangent line has slope maybe -1. So f prime of 2 would be -1. And we'll plot 2, -1. Moving to 3. Looks like the tangent line has slope maybe -1/2. So f prime of 3 would be -1/2. So we'll plot that point. And from here on out, you can tell that at 4, 5, 6, and 7, the slopes of the tangent lines there are going to be 0. So f prime of each of those values is 0, and we'll plot those points there. So connecting the dots here, we have a graph of y equals f prime of x. It looks like this blue graph. It's 0 when the slopes to f of x are 0. It's positive when the slopes to f of x are positive. F prime is negative when the slopes to f of x are negative, and so on. So being able to solve a problem like this is significant because in order to do it, you really have to think about the meaning of a derivative. You're not just applying rules blindly. You're thinking about what a derivative means. And I think that's important.
That's about enough for now, so we'll pause here, but we'll continue in Lecture 18b with a technical issue called differentiability. And after that, we can get back to developing our list of rules. So I'll see you next time. Goodbye.